Hi, my name is Debbie Kitzler, and this is my lab report for the third lab of Physics 2212, in which we observed the magnetic field of a bar magnet. In this lab, our goal was to establish that the magnitude of a magnetic field proportionally changes with its separation distance from a given source, and we wanted to understand this further. We used our cell phone and an app to study the magnetic field produced by a bar magnet. We determined the net magnetic field as well as the magnetic dipole moment. We observed this magnetic field at 3 different positions: on axis, perpendicular, and at a 45-degree angle off the axis. Then we utilized our data observed to use a Glowscript code to computationally model this, and then we also compared our Glowscript results to the results recorded by our magnometer app. The important physics concepts that we utilized in this lab were the Biot-Savart law, as you can see here. We also used the distance dependence equation for the magnetic field, and because this is hard to see, we also took the natural log of this equation in order to better receive a model of it, as I will show later on. We also utilized the equations of the magnetic field of a dipole, which I placed on the screen here. Part 1 of this lab focused on measuring the on-axis magnetic field. We compensated for magnetic north and also located the magnometer chip on our cell phones. We then moved the bar magnet at differing distances from the smartphone, as I showed here below, and recorded the distance at which it read specific values. So the values we looked at were 20, 70, 120, 170, and 220 micro Teslas, and we recorded this data in a spreadsheet in order to have a better way of modeling this data. So first we plot the ln of Bx versus ln of r, so the natural log of the magnetic field versus natural log of the distance, and found the slope-intercept of the best fit line. We then utilized the equation below for B in order to determine the magnetic dipole moment. So here's the data that I obtained in part 1 of the lab. The data I obtained in part 1 resulted in an n value which was equal to negative 2.85 or 2.84, as you can see here. This is very close to our expected value of negative 3, producing only a 5% error. I then solved for the magnetic dipole moment using the Biot-Savart law, and that resulted in a magnetic dipole moment of 2.85, which I will use later on. Also notable is that the average perpendicular distance was 0.18 and the average magnitude of the magnetic field was 1.2 e to the negative 4 Teslas. Part 2 focused on measuring the off-axis magnetic field, so we utilized a similar protocol. We moved the bar magnet at a distance until the smartphone read a specific measure of micro Teslas. But then we moved the phone upwards the same perpendicular distance and then recorded the new x, y, and z components of the net magnetic field. We also adjusted this to account for the net magnetic field of the Earth on the y component, and we repeated this 3 times to obtain the results, as you can see below. In this portion of the lab, the average perpendicular distance was 0.2555 meters, and the average net magnetic field was 0.00018 Teslas. The last part of this lab asked us to create a Glowscript code to model this phenomenon, so I utilized my results from part 1 to obtain my K value of 5.7 e to the negative 7. And then I created the magnet at the origin and used the equation for the magnitude of the net electric field that I showed earlier, as well as just setting up the vectors for my observation. And then here you can see how I actually positioned all of my new arrows to represent the magnetic field at various distances and various positions. I will link this Glowscript code in the description so that you can look at it more thoroughly if you would like to. As you can see here, my Glowscript code resulted in results very similar to the ones I observed. Our average perpendicular distance were very, very similar at 0.255 meters. And my experimental and computational results for the magnitude of the net magnetic field differed slightly, as you can see above, and perhaps this is due to human error in measurement or incorrect accounting for the Earth's magnetic field at various points. Lastly, a few questions. What if we hadn't oriented our experiment to compensate for magnetic north? If we hadn't compensated for magnetic north, then the x component of the magnetic field would not have been 0 in the beginning. both the X and Y components would have been impacted by the Earth's magnetic field, so we would not have been able to accurately account for it, and therefore we would not have been able to obtain data that was reflected only the magnetic field of the magnet. It would be due to the magnetic field of the Earth as well. And if we were to stick two identical magnets together end to end and run the experiment again, I would expect the magnitude of my measurements to increase by close to a factor of 2, while the direction would remain the same. Thank you.